We'll start very soon. I'm downloading the slide. So just some question first. I noticed that in my surrounding there's some noise. So is that noise disturbing? Because I heard some kind of hitting, just like this kind of sound. Oh, by the way, can you hear me? Okay, okay. Is the noise very disturbing? The noise outside my room? Oh, okay, fine. And, let's start. Okay. Now, today the schedule will be like this. First, we'll cover the topic of facility location games, and then we will explain the tutorial material, tutorial 2. And meanwhile, I'll also open the submission for in-class exercise 2. Okay. Now, up to now, we have covered one, or maybe I should say 2. Okay, we have covered 2 scenarios of mechanism design. One is in auction and matching. The second one is in fair division, right? Okay, so today is the third one called facility location games. And to just briefly remind you of some concept which have already been explained in the guest speakers lecture. Okay, so basically we, in this topic, we'll focus on the so-called mechanism design again. And then mechanism design basically will take input from agents and then decide an outcome. All right, now here we can consider this S1 to Sn be the agent's private information. Okay, so this is a private information, and then agents can report some information which is not necessarily true. Now the one that are reported is this one, okay, R1 to Rn. And then the mechanism will choose an outcome, and this outcome is based on the reported information R. And then each agent will have a so-called valuation function. So for example, agent I will have a value function Vi on outcome. Okay, for example, for outcome 1, his value is 1. Outcome 2, the value is 10, etc., etc. Okay, and then what's the purpose of the mechanism design? The purpose of mechanism design is to try to prevent agents from cheating about their true information. So in other words, if the mechanism is not designed in a good way, then agents may manipulate its reporting some false information, such that he or she will gain by this misreport. Okay, and then the purpose of mechanism design is to prevent this kind of thing from happening. Okay, so basically it tries to achieve a goal that if agents misreport, then he or she will not gain any more benefit, okay, compared to when he or she reports truthfully. Okay, and then here we are, in other words, we are trying to make sure that telling the truth is a so-called dominant strategy of agents. Okay, so you see that all the previous concepts, they are also naturally linked together. Yeah, you're right. So we hope every agent, its RI is the same as its secret information SI. Okay, so this is a mechanism design's purpose. All right. Okay, and then in mechanism design field, there are 2 major categories of problems. One is called mechanism design with payment. Okay, so with payment means, okay, after you select an outcome, then you can ask each agent to pay some money to the central decision maker. All right, in other words, there is a payment vector, P1 to Pn. All right, and then after the outcome is decided, what's the agent's utility? His utility will be his valuation, right? The value function minus his payment, right? Okay, so that's the net gain of an agent. So in the guest lecture, you already see, well, actually in auction, they are using some kind of mechanism design with money, right? So because when you buy something, when you bid for something, you need to pay in the end. Okay. Now, mechanism design with payment, usually one can use VCG. Now, actually, we also cover VCG today, okay, in the tutorial. And well, in a large class of problems, it will be relatively easier because you can use payment to kind of leverage the agent's gain, right? So you can say, oh, if you cheat, probably you need to pay more, and then probably you will not cheat anymore, right? Okay. Now the second class is called mechanism design without payment. Without payment. So without payment, that means there's no money involved. So agent's utility will just be the same as its value. Okay. How much he or she thinks the item is worth, then it's how much he or she gets. Okay. Now, we have quite some terms for this dominant strategy. So agents telling the truth. Okay, so if telling the truth is dominant strategy, then usually we say the mechanism is strategy proof or incentive compatible or truthful. But the detailed definition of strategy proof and the truthful is slightly different. Okay, so there's a minor difference here, but in the facility location setting, there's not much difference. Okay, so basically anything that is strategy proof is also truthful. Okay, now the major difference here, I can mention a bit, is basically about whether you assume other people are telling the truth. Okay, so usually strategy proof require that agents will not benefit with the other people's true information there. Okay, so so this is as far as I remember. Okay, and then truthful means that no matter what others report, I will tell the truth. Okay, even they report false information, that's fine. Well, of course, now this is only my understanding. It can be wrong, all right? So it can be reversed. But as I said, again, in facility location problem, it's the same, all right? Strategy proof and truthful, they are the same. Okay. Yeah, so I guess that at least on this slide, it's reversed, right? It says that no matter what others report, then, well, you're telling the truth is good. So it basically means that strategy proof means that you do not care about what others report. And then truthful, and then it's the other, then very likely it's the other one, right? Okay. Now we come to the definition of the problem. So what's a facility location game? Now, facility location game, there are a bunch of agents, and these agents have a private location, and we can say they are Xi. And then in the end, you want to locate one facility at location Y, okay? And then, well, the agents benefit, what's their benefit? Well, their benefit is usually their distance towards the facility, okay? So the larger the distance, the less benefit they will have. So, well, everyone tries to minimize the distance to the facility. All right, okay. And here we want to design mechanisms which are strategy proof for agents, right? And at the same time, we want some social objectives to be as good as possible. So this is the basic setting for facility location games. Now let's look at one example, okay? So the one possible objective for the society is to minimize the so-called social cost. Okay, so how is social cost defined? Social cost is defined as the summation of each individual's cost, all right? And then each individual cost is just their distance. So you see that the larger the distance, the larger the cost. And therefore we want the cost to be small, right? Okay, now see, this is a very, very fundamental example, it's a toy example. Now, what's the possible mechanism to optimize the social cost? So this is my first question, all right? Imagine that you have 4 agents, X1, X2, X3, X4. And then you want to find some location such that the 4 people's distance towards that location, if you add them up together, it will be as small as possible. Where do you think that location is, or that location can be? Okay, so I see a lot of answers, right? Now, somebody answered the midpoint. some of you say median. Okay, so now it's a half-half, right? Okay, so basically, in this example, middle point seems fine because somewhere here. Well, to make the analysis more rigorous, it should be something like this. So you usually will pair up agents, two extreme agents here, and then this, well, second last extreme. Okay, so you pair these agents together, right? Okay, you pair these agents together, 1 with 4, 2 with 3, and then say, okay, where do I put my facility? My facility can be put here, that's fine. But when you evaluate the total cost, now we try to add up the distance to the two partners in the same group. For example, x1, x4, okay? So x1, x4, their total distance towards the facility will be at least the distance from x1 to x4, right? Okay, so it cannot be smaller, it's not possible. Now, when can this minimum be achieved? Only if you place the facility within the interval x1, x4, right? Okay, so this tells us, at least for this pair, in order to make it smaller, you have to put it within the interval x1, x4. And then the same argument can go for the pair x2, x3, right? So similar story. The facility, which can minimize the distance total towards x2 and x3, it need to be placed within interval x2, x3. Yeah, very good. Any point between 2, 3, right? Because if you put it inside that interval, then the distance sum will be the interval length. If you put it outside, then the distance sum towards x2, x3 will be larger than the length of x2, x3. Okay, so that means, again, you need to place it within interval x2, x3. So this argument can go actually for all the pairs, right? So you have a boundary pair, middle pair, further middle pair, further middle pair. So eventually you will squeeze into the central pair, and then you place it in any place in the central pair, that will be fine. Okay, so that's exactly the concept of median, right? So median is a middle agent. So if you place it in the middle agent position, then very likely or definitely it's okay, right? Okay. Now I see one question from Xinran. We are considering four agents. Maybe we need to pick the furthest one. Okay, so now my argument will have a definite answer when you have an odd number of agents, right? So if you have 3 agents, 5 agents, then you will be placed in the middle agent, right? Middle agent, not middle point, middle agent, or in that case, it's also the median agent. But when you have an even number of agents, then median, in the sense of statistics, I remember that median means the summation or the average value of the middle two, right? Okay, but here actually you place it anywhere between x2, x3 will be fine. All right, the cost didn't change, right? If you place it anywhere between x2 and x3, the result is the same. The total distance is the same. Therefore, we have many choices. But mechanism has to, now here at least, the mechanism has to have one unique output. So we have to decide, okay, when you have an interval, right, where you can put it, then I would like to choose, for example, the leftmost median. Okay, so when you have 2 middle agents, I put it on the left one. Okay, that's still okay, right? That's still okay. So I would like to use this time to a very brief survey. Okay, so you get the point of how to find optimal solution for the very basic facility location problem. Okay, try to minimize the distance to all the agents. Okay, so the majority of you got it. Still several, very few didn't get it, but it's fine. I guess gradually, when I move on, you will know more, right? Okay. Now, Wing Chun asked a very interesting question. So there's some kind of fairness problem, right, between the middle two agents. Well, here, indeed, if you choose the left one, then the right one will say, it's not fair. Why not me, right? Well, but at least for now, at the starting point, we didn't touch the fairness issue yet. Okay, all right. And then, yeah. So Jianzhong, you are right. Here we define the median agent. I mean median. Okay, MEDIAN. Median agent means the the left one of the middle two agents. Okay, so you have two middle agents, and the left one will be that median. Okay, so will be the output we are looking for in this scenario. Okay, so at least for now, you will have a rough impression that optimal solution seems very easy to be obtained, right? So now let's see how good this optimal solution is. Now, in other words, let's check whether it's strategy proof or not. Okay. Now, in order to check strategy proof, we can do the following argument, which is very interesting. You see that we now place the facility at X2, right? So there are people on the left of X2, on the right of X2, and also X2. So one thing is for sure, X2 has no incentive to misreport because he already has a cost of 0, right? X2 has the facility on himself. So he's very happy. He said, okay, I will not cheat. If I cheat, I cannot get more, right? Because I already have a minimum cost. That's very, very good. Now, how about people on the left of X2? So let's look at this range. People here. So these people, you can imagine if they misreport. If you misreport to be still within this range, then they will not change the output because the middle agents didn't change, right? So if somebody on the left of X2, they say, oh, I changed my position. I'm not here, I'm there, but they are still on the left of X2. Then basically the position of X2 isn't hurt. There's still some kind of middle, right? Middle left. So output is still there. Now for these people, they will not cheat, right? So they will not cheat, at least they will not cheat to be still on the left of X2, right? And then you may say, maybe they will cheat to be on the right of X2. In other words, they are somehow cheating to be there, right? Okay, well, so now Wing Chun will notice that it's worse. Why? Because if you move somebody to the right, then the middle agents also move to the right. So basically, if you misreport to be on the other side, then you push the median away from yourself, right? The middle point of the whole set of agents, it also moves to the right. And therefore, you see that for people on the left, misreporting can only push the median agent farther away from himself or herself, right? Okay, so with this argument, you can see, people on the left, they will not cheat. And similarly, you can argue for people on the right, they will also not cheat, right? Now, overall, nobody will cheat in this setting. You can safely adopt optimal solution here, right? The left of the middle 2 points, okay? Or when you have odd number of agents, it's just the middle agent position, right? Okay, so any question up to now for this very, very basic scenario? So now you see that actually we explained why nobody will cheat, right, in this mechanism. And also, actually, we have answered the second question, approximation ratio. So what is the approximation ratio here? Oh, very good, 1, right? It's optimal solution. Okay. So this is the first one. Now feel free to ask questions. I believe the first one is quite, easy to capture, right? And actually we have a second example, which can explain the other extreme. We'll go to it very soon. Now for this one, actually it's the formal description of this mechanism comes from Prakacha and Tenenholz's paper in 2009, EEC, which is top conference in theory. And then they show that this mechanism, which outputs the optimal solution, is strategy proof, right? Okay, so just as we discussed just now. Then come to another objective. And this objective is also very well recognized. It's called max cost objective, okay? So max cost means what? So now we are somehow caring about fairness. So some fairness, what is that? Well, just now we are doing sum, right? Adding all the costs together. So now we say, maybe adding all the costs together is not good. We try to minimize the maximum cost. We hope that the person who is very unhappy about the outcome is not very, very unhappy, okay? So we hope that the extreme person is relatively happy, all right? Now remember that in the fair division, we also mentioned this one, right? About the social welfare, right? So we can do a sum, we can do a max, and there we call the objective some kind of a utilitarian, egalitarian, remember that? Okay, so just another term, okay? So here we just say total cost, max cost. So now the second objective, we are trying to minimize the maximum cost, okay? Now, again, one example, very easy example. So this example, we have two agents. One is at 0, the other is at 2. Now, if we want to minimize the maximum cost, where is the optimal solution? Oh, very good. Now this time it's really middle point, right? It's really middle point, because if you place it in the center, right? Or in the, well, let me find the cursor. So here, 0 is here, 2 is here. Optimal solution is 1, because you move it far away from 1, right? Either on the left or right, one party will be less happier, right? Okay, so middle point is the optimal solution for max cost. So now we come to the discussion about strategy proofness, right? So is this strategy proof? Will somebody misreport? And the gentleman said no. Okay, oh, very good. Many of you say no. Why no? Okay, actually we have very easy to observe manipulation, right? So the person on 2, he says, okay, I cheat to be on 4. Now, if I'm on 4, you see between 0 and 4, the middle point is 2. Okay, now 2 is very good for x2, right? So because x2's true location is 2. So if he misreports to be farther away from 0, and then the facility will just be moved towards his true location, and then his true cost becomes 0, right? So the person at x2, he has some incentive to lie, right? Okay, no, that's not good, because as we said, strategy proof is some property we really targets at, right? Okay, so we say, I hope that they will not be able to lie, because well, if you simply go for the optimal solution, which is middle point, then the right person can lie and drag the facility towards him. That's not good. So then what do we do? Now, in order to guarantee strategy proofness, now one suggestion is, how about we place the facility at the leftmost agent's position? In this example, we place it at 0. Okay. Now, placing it at 0 is strategy proof. What's the reason? Now, you see, actually, again, we divide into two cases. One, will this x1 person cheat? Now, the answer is no, right? Because, well, x1 already achieved a cost of 0, so he will not cheat. Now, how about people on the right of x1? For these people, again, similar argument. If they cheat, they're still on the right. Then basically it's useless, because they will not affect the mechanism's outcome, right? Well, the only exception will happen when they cheat to be on the left of x1. But if they cheat to be on the left of x1, then the facility will be moved to the right, to the left, right? To the left of 0. But that will not be good for them, because it's farther away from them, right? Okay, very good, Cindy, right? Okay, so you see that it becomes worse. So it becomes worse, then why will they cheat? Okay, so basically they will not cheat, right? They will not cheat. Now, on the other hand, we now know nobody will cheat, but will this solution be good? Now, actually, this solution is relatively good. Why? Because if you place the facility at 0, then what's the maximum cost you get? It's the length of the interval x1, x2, right? So it's 2. Now, what's your optimal solution? Optimal solution is what? You place it in middle, right? And the point is, the distance is 1, max distance is 1. So what's the approximation ratio here? Okay. So the approximation ratio will be 2, right? So as many of you have pointed out. Okay, so you see that this mechanism, placing the facility at leftmost position, it is strategy proof and has an approximation ratio of 2 compared to the optimal solution. Okay, so with these two examples, basically you know the basic framework of the research questions or problems people consider or care about in facility location games. So basically, they want to achieve the strategy proofness. At the same time, they want the solution to be relatively good, right? Okay. Now Jiang has one question. Total cost. Now remember, now we are talking about max cost. So if you place in the middle, the max cost is 1. Okay. I agree. Total cost is still 2, but max cost is 1. That's why we say approximation ratio is 2, right? So now we are talking about max cost. Okay. Yeah, I hope it answers your question, right? Okay, so Xinran is asking also a very why max cost is 1. Okay, because if you place at 1, agent here has a cost 1, right? And agent here has a cost 1. So the maximum cost of these two is 1, right? Okay. Okay, now Xinran's question about whether we should disregard agent's report information and place a facility. Well, actually, not quite this case, because you see that if we put it on the leftmost agent's position, we still take the report into consideration because that position, leftmost, is also reported by agents. We didn't ignore agent's report. We still need to consider agent's report, but well, we are consider the report in some special way, right? So some people's report is very important. I consider it, right? Others, well, forget, right? So you are not important, okay? So that's the rationale behind it, okay? Yeah, so any question up to now about the social cost, optimal strategy proof? Max cost is a to approximation, right? Strategy proof, but to approximation. So I'm not going to do the survey this time. I believe that yeah, more people will understand, more students will understand this point, right? With when we talk about max cost. Okay. Yeah. Xinran, actually, you are raising a very good point. Indeed, if your output is a fixed location, then nobody will cheat because it's fixed, right? So actually, there are a bunch of mechanisms. Especially in one scenario where people call something like false name proof. So I will probably mention it in the very end of the topic. Now, for that kind of manipulation, only fixed point will work. Okay, if you place it anywhere else, as long as you seriously consider agents' locations, then you will not do anything good. Okay, so that's a very, very important point, okay? So there are mechanisms where you place the facility at the fixed location. But if you place the facility at the fixed location, then usually the approximation ratio will not be good, okay? Usually, all right? Because you disregard agent's input, right? Okay. Well, yeah, fixed location is very difficult to optimize, you know, right? Because agents can be anywhere. And then your fixed location, no matter which fixed location, I can always give you a profile of agent's location, which make your ratio very, very bad, right? So here, it's very difficult to optimize the fixed location. But that's a very good point. I will come back to it when, as I promised, in the end of the lecture when we talk about variance. Okay. Yeah. So this is again from that DEC paper, the same paper. They show that placing the facility at leftmost point is to approximation, right? And then at the same time, they show something more. They say any deterministic strategy proof mechanism cannot achieve a ratio better than 2. So basically, the one we explained is the best possible. Nobody can achieve better things. So this is again some message I have delivered to you when we talk about algorithms. So in algorithms, especially, well, approximation algorithms, we also have similar story, right? You say, okay, your algorithm is to approximation. And I can show that no deterministic polynomial time algorithm can achieve approximation ratio better than 2. Then yours is the best, right? So if you can provide such kind of lower bound, then you are making your algorithm at a strong position, right, in this problem. Okay, so here, same story, right? They show that nobody can do better than 2. So their mechanism is the best possible, right? Okay. So these are the 2 basic things. Now, of course, they also design some other things. For example, they designed randomized mechanism. Now, randomized mechanism, I will explain them very soon when we move on in this topic. But for now, I guess you can have a rough idea about what randomized mechanism is. So basically, with some probability, choose some location. For example, what they design is that with quarter probability, you choose leftmost point or rightmost point. Okay, so leftmost quarter, rightmost quarter. And then I have half chance, half probability, choosing the middle point. Now this mechanism, they prove is 3/2 approximation, which is 1.5, right? For the maximum cost. and you see that this one is better than 2, right? And then you may say, it somehow is contradictory. You said that nobody can do better than 2. Oh, am I wrong? We said that the lower bound is 2, right? Okay, so the point is here we are talking about randomized mechanism. Lower bound is for deterministic mechanism, right? You can only output one location, right? So that lower bound is 2. But now we are doing randomized mechanism. So that's why we say it's not a contradiction. 1.5 is better than deterministic. It's totally possible, right? Okay. All right. And then the same paper, they also have some other variants. For example, study 2 facilities, 2 same facilities. All right. And then one agents only need to be served by one of them. All right, because they're same. And then there's also a version where they study 1 agent controlling multiple locations. Okay, so basically it means that 1 agent can report, for example, 4 locations. He controls 4 houses, so he can report 4 locations to the system. And then his cost is the summation of the distance to its own 4 houses, right? Okay, and then this version, they also have some results. Okay, so that's just briefly summary what we have now. Now we have an objective. Social objective is either social cost or max cost, right? Mechanisms, we can have deterministic mechanism and also randomized mechanism. And later on, we'll show randomized mechanism, you can have truthful expectation mechanism and also dominating truthful mechanism. So there's some kind of difference between these two. And then approximation on objectives. Well, you can have some upper bounds, right? How good your mechanism is, and also lower bounds. Yeah. Nobody can do better than a certain bound, right? A certain ratio. All right. And then further thing, they have some extensions, right? From one facility to 2 facilities, or maybe multiple. So at least they extend to 2. And also they extend the case of 1 agent controlling multiple locations, right? One person has many locations. Okay, it seems that, well, it's very, very classic paper and the story is just complete and then maybe the whole game is over, right? Okay, now, is it so? Actually not, all right. So let's see why not? Because just now we say people want to be close to the facility. But actually, there is also another extreme. So another extreme is everybody wants to be far away from the facility, right? Okay. So what kind of facility people do not like it? Well, for example, a polluting factory, right? Pollution is not good, right? And also a garbage dump site, okay? So that site, you need to use it, but not too close because it's smelly, right? And also something like prison. Why prison is good, bad? Because prison is in case of accident, it will be quite dangerous, right? Okay. Now these facilities, people want to avoid that. Sometimes they also need to use it, but they want the facility to be away from it, right? Want their houses to be away from these facilities. Then this model, algorithmically, was studied by Guochen Zhang's group in Zhejiang University, and they proposed the following mechanism. They say, okay, let's vote. All right. Now, because for this kind of you want the facility to be far away, basically you need to limit the positions the agents can be located at. They can no longer be anywhere on the line, and also the facility cannot be anywhere on the line. Why? Can I still allow facility to be anywhere on the line? Yeah, so Jianhuan, you're right. So because then it's infinite, then I can just put the facility very, very far away. No limit. Okay, so you can infinitely increase your distance, which is good in this case, right? In this obnoxious facility location game, it's good, right? Okay, so basically you cannot say I have no limit of the line. Therefore, we say we have to limit the agents to be located within an interval, say 0, 1. Okay, and then say everyone is inside 0, 1. And then where do you put facility? Well, very naturally, you would say I would like to place it on the extreme point, right? Well, it seems always good. It's a facility either here or here, right? And then comes the voting mechanism. They say, okay, please, everyone vote. Who like 1? Who like 0? Okay, and then you can imagine that people on the right like 0, right? Why vote for 0? And people on the left like 1. Okay, so let's just see which side has a majority. Okay, who has a majority? I just follow whose suggestion, right? Okay, so this is the mechanism designed in their paper. All right, okay, and then they show that this mechanism has an approximation ratio of 3. Okay, now is a bonus question. Why this is not optimal? It seems a bit strange to me, right? I think that based on voting, it's very natural that it's optimal, right? Because I'm following majority's opinion, so I'm being very nice, okay? Okay, so Jiang Kun, you got the bonus. Okay, now basically, the point is what? The point is, let's look at the line segment again. People who like the right point, they may be very close to center, like the example used by Jiang Kun, right? Okay, they can be very close to this point. Okay, so for them, right point and left point actually doesn't matter, doesn't differ a lot. Their distance is just a minor difference. Although they slightly prefer the right point, but left one, they are also fine, right? You may imagine that those who like left point, they are at the extreme. They're here, right? Okay, for them, it matters a lot, right? If you place on the left, cost is huge. Everyone has cost 1. If you place on the right, everyone has cost 0. Okay, so for them, it's a difference. Remember, you are doing voting, so you do not take this distance difference into consideration. And therefore, this is not optimal solution, right? Okay, and then you'll ask a very good question. If there are only 2 candidate locations, why not just enumerate? So I guess you mean, why not just, how to say, compute how good each solution is, and then I choose the better solution, right? Okay, well, of course you can do that, but that will not be strategy proof, okay? Here, voting is strategy proof, because you can imagine if somebody like facility to be on the right, he will never vote for left. Voting for left will be harmful to his own group, right? Okay, it will have less chance making the facility on the right, and therefore nobody will risk voting on the opposite side. But if you take the optimal solution, then people will manipulate. Okay, now of course it's possible to find example, but I guess I will not find example here. You are encouraged to find one, but I'm not going to make this an in-class exercise. Okay, so just out of curiosity, you can try. Yeah, so now this is the picture about obnoxious. And well, now let's see whether it's a complete picture now. Okay, it seems that we have people want to be close to the facility, and also we have the version where people want to be far away from the facility, right? Okay, now it seems to be a complete story. So is that so? No, actually, again, not. Now this is also when my group starts to investigate this problem. Okay, so we start to investigate the problem. Well, before we see the obnoxious comes a bit after that. We start exploring along this direction first. Now, so the one very natural extension is something like graph problem. So when I tell you about the problems on graphs, then very naturally, every vertex and every edge, not only they can serve as one count. For example, I'm one vertex and this is one edge, but very naturally, you can associate a so-called weight to edge or node, right? Just like if you want to compute the shortest path problem, you can have a unit length, right? Unit length edge for every connection. You compute the shortest path, but when you, in that scenario, you only need breadth first search to figure out the shortest path. But how about if I link a weight to each edge, and then you want to compute shortest path? Then you have to use the Dijkstra's algorithm, right? Okay, so weight is a very natural extension to graph problem. And then similar stories happen here. Weight will also be very natural for our agents. Okay. Now, here we talk about two versions. One is weighted agents. The other is threshold-based agents. And I will tell you the story about threshold-based agents very soon. Now we start with weighted agents. What is weighted agents? Actually, very easy. You see, when I define the cost, I just multiply a weight, WI, on top of distance, right? And that means if an agent has a high weight, then his cost will be high. Okay, so this is a very natural weighted extension of the facility location gain, right? Okay, so now, actually, for this version, we have some results. So the results is the following. We prove that, well, actually, weights cannot view the possibility of designing better mechanisms. In other words, the best mechanism when you have weight is to ignore weight. Now, of course, here we assume weight is private information. Agents can cheat about weight. All right. So now you can imagine that if agents can cheat about weight, very naturally, you cannot take weight seriously. Why? Because if you take weight seriously, then the agents can just misreport his weight to be arbitrarily large. And then because you are taking weight seriously, you have to move closer to that misreporting agent, and then the strategy proofness will be gone, right? It's very natural to imagine this. Yeah, so Xuezhen, you're asking a question whether you can cheat about weight and position at the same time. Yes, the answer is yes, okay? So in this model, we assume that they can cheat both weights and locations and positions, okay? Yeah, so will the weight influence the monotonicity? So Xina, I'm not quite sure what you mean by monotonicity. Now, maybe I would just move on a bit. Xina, you can explain your question in more detail, all right, about monotonicity. Now, the results we obtain is the following, which matches the results for the unweighted case. Basically, we say median mechanism, which is mechanism 1, okay, can achieve the maximum weight over minimum weight approximation. So this time, approximation ratio is dependent on what? On the weight, right? So if your weight difference is huge, right? Large weight and small weight has a very huge difference, then the approximation ratio will be very bad, right? The news is we can also show this is a lower bound. No deterministic mechanism, very proof 1, can achieve a ratio better than max weight over mean weight. Okay, well, so that basically closes the gap, right? You cannot do better than that. So this is the best. The mechanism 1 is best. Mechanism 1 basically ignores weight, right? Median agent only. And then we also show that mechanism 2, which is the leftmost point mechanism, is max over mean plus 1 approximation. You see that these two results, when weights are the same, this one is optimal, right? 1 over 1. And then this one will be 2, right? Because when weight is the same, this division will be 1 and plus 1 becomes 2. So it's a 2 approximation. That matches our earlier discussion, right? Okay, and then we show that nobody can do better than this still. Well, so it seems that, well, the results, although we show that, well, if you have weight, you cannot do better than ignoring the weight. And then we also show the lower bounds. But unfortunately, when we submit the results to some journal, which is, to some journal, we have one recommendation of reject, saying that, oh, these are too straightforward, okay? So everybody knows, if you can misreport the weight, you cannot take weight seriously. So the results, although they are tight, they seem to be less impact, to have less impact. Well, now, of course, when you receive comments like this, you will feel a bit frustrated, but still we respect the reviewer. So that also triggers us to consider one other variant of the weighted model, which is very interesting. And then that one finally, well, makes the submission successful, the revision successful. Okay, so let's go to the second weighted model, which just come up after we receive the reviewers' comments in the first round. Okay, so what's the second one? Second one is threshold-based agents. What is that? Well, forget about these words. We just look at one example. In this example, you see that imagine a scenario where you are building a base station. Okay, base station is responsible for communicating with mobile phones, and everyone has a mobile phone. They are of different brand, right? They were bought in different years and they're manufactured in different years, so their receiving power is a bit different. Okay, so maybe some mobile phone is very powerful. It can receive signal from 2 kilometers away. Okay, so for those mobile phones, for example, this one, orange one, this mobile phone, the person who is holding this mobile phone says, okay, as long as your base station is within 2 kilometers, then I'm fine. I'm satisfied because I can receive signal without any problem. All right. Okay. And then there are some old brand of mobile phone. The green one, it says, okay, my mobile phone is not that good. All right. I can only receive signal when your base station is within 100 meters from me. Okay. Well, so for this kind of person, you see his acceptable interval is shorter, right? All right. For those strong mobile phones, there's very large interval size. Now, what's the problem? So the problem is how to locate the base station to satisfy as many customers as possible. Okay, so this question, why do we say it's related to weight? So you can imagine that a person or a mobile phone has a high weight if his receiving radius is very small, right? Now you can say, oh, I'm only this tiny interval, okay? Only if you place it within this interval, you can satisfy me, okay? Well, so that means he's in now if you want to satisfy this guy, and then you have to move very close to it. And then that means he's very important, right? So basically interval length is some kind of importance indicator, right? You're more important, then your interval can be narrower, right? Shorter. Okay, so this version of the problem, we prove some results. Okay. Now, can anyone guess the result? What kind of strategy proof mechanism is possible? So remember, our objective is to satisfy satisfy as many intervals as possible. Okay, so I see some suggestion. For example, Jian said overlap most. Okay, yeah. So which means, well, we are going for the so-called optimal solution, right? So where is optimal solution? Optimal solution is a place which intersects the most number of intervals, right? Okay, so I just place the facility there. But there could be many such points, right? Many such points. So where do we put it? We have to break the tie, right? Very good. Okay, Wing Chun said just leftmost, right? The leftmost point where of all the points who has the largest overlap, right? Intersect with many intervals, the most number of intervals. Among them, I picked the leftmost. And this is indeed the mechanism we designed at the time. Okay, well, we are able to show this mechanism is strategy proof. Now, optimality, we already showed it, right? We are using some optimal solution, but at the same time, we're able to show nobody will cheat. So actually, nobody will cheat is also very easy to see. Why? Now you can imagine one interval. For example, this one, or maybe the orange one, okay? One interval. So suppose somebody cheat. That must be the case that the facility is not in his interval, right? If it's in the interval, he will not cheat. So it must be the case that the facility is somewhere outside interval, either here or maybe on the right. Okay, now let's see whether he can try to bring that facility back into his own interval. Is it possible to move it in? Well, the answer is no. Why? Because you see, cheating will only decrease the count in his true interval. Will decrease it, right? Will decrease the count. And probably increase the count outside. So with this kind of change of those counts, you can see that earlier, this one has the largest overlap. After misreporting, largest overlap will never come inside. That's not possible. Okay? It can only be moved around in the outside area. It will never come inside. So that's why it's strategy proof. Now, of course, I'm using a high-level idea to prove, but I believe it's not difficult to write down a rigorous proof, right? Okay. Yeah. So this is the. Yeah. You're right. It's binary. Each agent is either satisfied or not satisfied. So it's only two cases, right? Either inside interval or outside interval. How long? How far away? I don't care, right? If you're outside by 1 meter or outside by 1 kilometers, to me it's the same, because in both cases I cannot receive any signal. So why bother, right? The same utility. Okay. Yeah. So I guess we will take a 5 minutes break and then we come back. Now, in the break, I would like to do a survey. So did you follow most of the materials we talk about in the first hour? Yes or no? Let me see. Sorry, I need to relaunch the poll. Okay. Yes or no? You follow most of the materials we covered in the first hour? Okay, and I see a majority is fine, but still there are some students who didn't. Now, please do send me some messages, private messages probably. Let me know which part is not clear to you, all right? Because, well, I will only talk about the technical things in the first hour. In the second hour, I'll not talk about technical things. The rest of it, they will be easier to capture, but I still want to make sure that you can at least understand the basic part, all right, with the technical materials. So, yeah, so feel free to send me messages during the break. Oh, again, mic problem. That's weird. I probably will unplug the microphone, the headset, and try using the computer, because I just recently borrowed another one from the lab, and well, it's a new one, so I hope it's better. Okay, so now I'm using the computer microphone to speak. Okay, I remove this. I hope it's better. I will not have this occasional problem. And let me know if my voice becomes vague again. Okay. Yeah, thank you for reminding me. Yeah, so especially because I noticed that about 5 students didn't get the most of the discussion in the first hour. Still let me know what questions you have that bothers you. Okay, I would like to make sure that at least for this topic, the basic one, everyone is able to capture. Yeah, Xujun is asking a question. The approximation ratio for this mechanism is 1. Yes, because we're using the optimal mechanism, right? Optimal solution to the mechanism output. Social cost. You mean the one here? This one? So which part is not clear about social cost? About is it whether it is about the optimal solution or about the definition? So the definition of social cost is the cost sum of all the agents, right? And then what's the cost of an agent? It's just the distance from that agent's location to the facility's location. Is it clear? So everyone, the distance towards the facility is the cost. And then social cost is adding up all these distances for each agent. And then similarly, max is the same. But the max cost means the maximum of all the agents' cost. Yes. So some mechanisms are designed for social cost and some are for max, because the mechanisms good for social cost may not be good for max, and vice versa, right? But there is one side note about the mechanism. Actually, you see that for social cost, we locate at median agent's location, right? So actually, this mechanism is also good for max. Right, this one is good for max. Why? What approximation? So the question is median agent, right? I place a median agent. This mechanism is also for max cost. What kind of approximation can be achieved? Yeah, so basically, again, no one can cheat, right? In the max situation, no one can cheat. And the ratio is 2. Yeah, very good. Jianwen said ratio is also 2 because leftmost is 2. Then any point in between the left and the right, they must be 2, right? Because they are even better, right? In terms of max cost. So the ratio is 2. Very good. All right. So basically, then it will possibly extend to another scenario or other possibilities, like I put the facility at the case location. So if I sort all the agents from left to right, and then put it on the case agent's location, this mechanism is also strategy proof. Nobody can cheat. And then it's also 2 approximation for max cost. Okay. So these bunch of this series of mechanisms, they are just the same. Okay, have the same effect for max cost. Okay, so we'll come back. Well, I guess my sound is still okay, right? Without headset. Okay. Now, just to wrap up, we have a mechanism, right? To as we just discussed, and this mechanism is optimal and is strategy proof, right? And then you see, actually, now it seems that the whole story is complete. You want the facility to be close? Yes, you have a version. You want the facility to be far away? We also have a version. And we have a weighted version. Okay, maybe at most we have a weighted version for obnoxious, right? So it was just, well, all the combinations happening here, right? So it seems to be a complete story. But is that so? So actually not, okay? The truth is, a new era has just begun, okay? With these exploration of facilitation games, many more will come up, okay? So actually, I can say half of my research recent years are on facilitation games. So that shows how rich this domain is. Okay. Now, just like any TV series, right? When you see this one is pretty successful, and then the first season is very successful, then the directors and actors, they could probably go on to the season 2, right? And then we know that there are many famous US drama. They have many seasons, right? Like something like Superman or other stories. Now here, research has a similar trend. Okay, so when the basic model is very successful or turns out to be very useful in practice, and then people can also come up with other seasons, right? So here for facilitation games, we have a bunch of seasons ahead. Okay, so we'll start with the second season now. Just now, we say agents can be close to the facility, could like the facility to be close, or like the facility to be far away. Now, can we further change agents' preference? Well, so the answer is yes. We have 2 works. One is about double peak, and the other one is about dual preference. Both of them are very interesting. Okay, so let's start with the double peak. And actually, double peak is the first breakthrough work along this direction, which also inspires our whole group to continue working on this. Now, what is double peak? Well, double peak is, now you can imagine here we are using school, but usually I would like also use a hospital as an example. So if I say I want to build a hospital in your neighborhood, do you want the hospital to be close or far away? No, Xingran said close. Many of you say close, right? Okay. So any objection? Okay, so Wing Chun said close, but not too close. Why? Because if it's too close, there could be some potential that many patients will come to the hospital. They will pass by your house, and then you have a higher risk of being infected by the viruses, right? So it's very likely. So you want the hospital to be close, but not too close. Therefore, there are 2 sweet points on either side of your house if your house is on the street. Okay. Now, the cost function of that facility will be something like the W shape. You know that earlier a traditional facility location game, we say it's single facility location game, right? Single peak means if you place it on the agent's location, it's best, 0 cost. And then, okay, so Xinran, you are talking about more necessity. Okay, very good. Okay, and then now when you get far away, then your cost will increase. And then if you get far away on the other direction, your cost will also increase. Now, of course, I need to answer Xinran's question. If you just wait, then definitely will affect the shape of this thing, right? So if you have higher weight, it becomes this, right? Very, very steep, right? If you are lower weight, it becomes flat, right? Okay, but it's still monotone. Now, double peak. If you put it on the agent's location, it's not good. Okay, for example, you put it here at XI. It's right on top of the house. It's not good. The cost is not small. If you move farther away, right? So like here, and then you decrease, right? Cost decrease until some sweet point on the left, and it stops decreasing. Because if you further increase the cost, then you will feel very inconvenient, right? Because the hospital is too far away. So the cost increases when you go beyond that threshold. Okay, on the other side, the same, right? Like this. Okay. Now this cost is agent's cost. It's not max, because we are not talking about the social objective. We are only talking about the agent's cost, right? What is agent cost? Oh, it's no longer distance. It's a function of the distance, okay? If the distance is small, the cost will be high. If the distance is not too small, medium, then the cost is low, right? And the distance is even higher, it's larger, then the distance become larger again. Okay, so that's the U-shaped or double-peaked reference. And here, I'm going to introduce some more useful concepts. Earlier, we mentioned strategy proof, which means a single agent will not cheat on his location, right? And then actually, we can also have something called group strategy proof, which means a group of people, if they misreport together, then at least one agent whose cost will increase. Or so there are different versions of group strategy proof. Here is one, okay? So if all the people misreport together, at least one of them will increase the cost, and therefore he or she will not join the group. So we hope that the mechanism can also achieve group strategy proof, right? Even a group of people cheating together, they will not benefit, right? They will not benefit altogether, right? At least somebody will lose something. Okay, and then the second property is the following. It's called position invariance. What's this? It says that suppose I move all the agents' location to the right by a same distance, t, and then your output of the location of a facility should also be moved to the right by the same distance. In other words, we hope that the mechanism's output will be position relevant. Okay, it will be based on relevant position, not absolute position. Okay, so if you shift all the people to the right by 1 meter, then my location of facility should also be shifted to the right by 1 meter. Okay, so this is called position invariance. And then finally, there's one property called anonymity. So this one is also very useful. It basically says if A and B swap their locations, and then the output should be the same, the mechanism should not treat agents differently. It should not be the case that because you are my friend, so I'm going to build a facility close to you, right? So this will never happen. If you swap the house, right? Swap two people's house or swap two people's locations, then the output should not change. It should still be the same. Coalition. Now here, well, this coalition here, you mean group strategy proofness? You mean this one? Actually, this is a general definition. Okay, so if there is one group of agents, they cheat together such that everybody is better off, and then they will cheat definitely, right? Or there is a weaker version where a group of people, they cheat together and nobody will be worse, but somebody become better and they will also cheat. Okay, so there are different versions of the group strategy proofness. And then this actually the coalition here can be any group of agents. All right, so we do not limit who can join together to misreport. Okay. All right. Now, in our paper, we show that there's no deterministic group strategy proof mechanism that is anonymous and position invariant at the same time. So basically, these three properties, they cannot be achieved at the same time for deterministic mechanism. All right, we have to sacrifice one. But you see the second one and the last one, they are very natural. So the first one has to be sacrificed. Okay. All right. So actually for Xiao's question, when we talk about strategy proofness, if you want to achieve strategy proofness, then you are already strong enough to defend against purposely collaborative cheat. Okay, so basically, if you say, my mechanism is group strategy proof, then people will say, then forget about grouping together and cheat because it's useless, right? It's not possible, basically, right? So group strategy proof can avoid or prevent this kind of cooperatively cheating. Okay, and then we have one mechanism. This mechanism is very similar as the extreme point mechanism, leftmost point. So here, because we are W shape, so we no longer have the leftmost position. Okay, instead we are talking about peak. So the mechanism says I can put the facility on the leftmost peak, x1 minus c. Okay, so that's the leftmost peak, and then or put it on the rightmost peak. And then we show that this is mechanism. This is strategy proof. And then actually, when you have only two people, only strategy proof mechanism that can satisfy the properties is this mechanism one. All right. Okay. Now, actually, well, as I just mentioned, right, in the single peak preference, if you choose the case agent's location to be the output, it's also strategy proof. But here in double peak scenario, it's not true. All right. We are able to show that in the case agent's location is no longer good to achieve strategy proofness. Okay, now we come to the introduction of the two important definition for randomized mechanisms. Now, as I said, we have two classes of randomized mechanisms. One is called universal truthful. The other is truthful in expectation. So what is universal truthful? Universal truthful means this randomized mechanism has several outputs. Each output, if you output it with 100% probability. In other words, if I just output that location, it is deterministically strategy proof. So I'm mixing those individually strategy proof solutions together to be a probability distribution. This is universal truthful. All right. Each individual candidate that may appear in your solution itself is strategy proof if you choose it with 100% chance, right, as an output. So yes, this is universal truthful. Now, because this universal truthful is very strong, require very strong property, and ratio, the approximation ratio will usually be bad. So in the double peak instance, yeah, so there one question about left peak, right peak. Yes, minus C is left peak, plus C is right peak. You're right. So now we have, just now we say, choosing the leftmost left peak is strategy proof. Choosing the rightmost right peak is strategy proof. And then I mix them together with probability, right? I say, okay, I use the probability P, output the leftmost left peak, right? And I use probability 1 minus P to output X2, XM plus C, right? Rightmost right peak. Now, in this, let's examine the mechanism 2P, okay, with the probability. And we show that if you make P equal to half, and then approximation ratio is N/2. The social cost is very bad, right? N/2. Oh, why? There's always a mic issue. Is it better that I use a headset? Yeah, maybe I speak too loud. I don't know. Yeah, maybe it's about Zoom. But anyway, let me just plug that. Probably still stable. Yeah. Okay. Yeah, is it okay now? Yeah, has it? No? Not good now. Okay. Maybe unplug it. Let me just check my voice audio setting. Okay, maybe I just oh, you mean I adjust the sound, right? Let me adjust, let me change it. In sync. Top left corner. Seems that I'm not so friendly with the. Maybe I first untick the automatic adjust option. I didn't find the original sound. That's a bit weird. Oh, not in the setting. Where is it? Is it okay? I untick that automatically. Screen top left. Screen top left. Screen top left. Oh. I still didn't find it, but well, probably we'll adjust that in the break of the second hour. Okay. Is it okay now? Near the recording. Let me see.
Hi, Professor. I sent you the Snapchat in the WeChat. You can accordingly set the.
Let me see.
Original sound.
Sorry for the well, unexpected voice problem. Music and the professor is also in the setting. Audio. Oh, okay. I see. I should untick everything. Should I take echo cancellation? Yes, right? Is the effect better? Is it better now because I click the? Okay, good. Thank you. Yeah. So let's continue. Okay. So just now we say a universal truthfulness is a very strong requirement. That's why the approximation ratio that can be achieved usually will be not that good. Okay. And then for this specific mechanism, show that it's n/2 approximation, which is very bad, right? Because n is number of agents. And then, but at the same time, we show that no other mechanism can do better than n/2. So basically, it's also tight, right? Okay. And then the second class of randomized mechanism is called truthful in expectation. And then truthful in expectation, the definition is the following. It does not require every individual point to be stereo-proof by itself. It only needs the fact that the expected cost will not decrease after an agent misreports. Okay, so basically misreporting will only have a chance to increase agent's expected cost. And then if an agent is very, well, somehow risk neutral, then he will not risk, right? So, okay, risking probably will give the agent larger cost, which the agent does not like, right? Although, well, with some probability, the cost can be smaller, but well, overall, it's not good. And therefore, we say if the mechanism is truthful on expectation, then it could, well, so because the requirement is a bit weak, right? It does not require every individual point to be strategy proof. So we can usually do better approximation. So here, what's the mechanism we adopted? Now it's a variant of the median mechanism. Here, XM is a median agent, and we are choosing one of its two peaks with equal probability, half. Okay, and then we show that this mechanism has an approximation ratio of 2 for social cost. Okay, yeah, so this is about randomized mechanisms. In the difference between universal truthfulness and truthfulness in expectation. All right. Okay, Xinan, your question is very good. Truthful in expectation, it means that agent's cost, or with some probability, it can decrease, but with some probability, it will increase. And therefore, the increase and decrease will somehow cancel each other. And then in expectation, it's not good. Yeah, just as you said, right? In expectation, it's not good. Okay. But indeed, if the agent wants to gamble, right? So okay, he said, I want to risk. Okay, I just want to risk because I have two solutions, right? This example actually we talked about in the online algorithm topic, right? So suppose I have one solution where the agent's cost is always 1. And there's another solution, the agent cost will be 0 with probability 10. And then its cost is, let me say, is it 10? Oh no, so agent's cost is 0 with probability 90, okay? But its cost is 10 with probability 10%. So basically, there's a small chance that his cost will be largely increased. But then there is also a dominating probability where the cost will decrease to 0. So if the agent is like to gamble, then, well, for a lot of times he can get the 0 cost, and then probably he will cheat, right? Okay. And then, but if the agent says, okay, I care about the expected gain, then he will not cheat. All right. Okay. So now welcome to the second episode of season 2. All right, that's called dual preference. And this dual preference. Oh, actually, I forgot to tell you the story about this double paper. And you know that this paper we submitted for the first time to the top conference EC. So actually, we have a chance there because we got 3.6 out of 10. So usually, you got a mark slightly above 6, it will be an accept. Now, and then there is usually rebuttal in the paper submission period, and then during rebuttal, well, because it's the first time we see this, we have this possibility, and then one of our co-authors he thinks that he drafts something and clicks submit before circulating to all the authors, and then the system says you can only submit once, and therefore, well, at the time, because it's first time, I'm also not experienced. I didn't contact the chair to update the rebuttal. Maybe it's not possible because if it's possible, they will allow multiple times, right? And then it turns out that with this very immature rebuttal, and then, well, some new reviews, they dropped their evaluation to 5. And then this paper didn't get in. And then this paper didn't get into AAAI in 2015. So basically, it just rests there. Well, cycling for 2 years before it's finally accepted. And those 2 years is, well, we gain a lot of experience, like we submit to one conference, and then we got a very high mark, like it's also a top conference. And then we get a very high mark, like a 998 out of 10. So we think that, oh, it's a sure in, right? But then before rebuttal, the chair sent a message say, your paper is rejected. And then we are very surprised. And then the reason is they say that conference does not allow appendix. But as a theory paper, usually we have appendix showing the proofs, and then we are attaching that. So they said that this violates the rule, and therefore directly rejected without any chance to answer the reviewer question. And then later on, we have other bad experiences submitting to other conferences, other lower rank conferences, all get rejected. And then finally, we also for the first time successfully get in AAAI with rebuttal, successfully changing 2 negative scores to 2 positive scores, and then we get in. And so this paper is the I can say the paper with most experience in all the papers I submitted in my academic career. Okay, so but this also actually I'm trying to share with you some information, right? So when you submit to conferences, if you are sure about the quality of a paper, then do not give up, right? You can try several times, and because each round you will get very useful feedback from the reviewers and improve your paper. And this is also the purpose of the review, the whole conference review process. Okay, so and Jian Chong asked a question, why picking the median agent in mechanism 3 is not group strategy proof? This detail, I guess I cannot explain here. If you're interested, you may refer to the paper. Okay, so we have examples there. Okay, so, but it's good to ask the question. Okay, yeah, then episode 2 also has a story. Episode 2 calls dual preference. So what's this? So actually the idea is very simple. Why? Because we know there are people who want to be close to facility, right? And there could also be people who want to be far away from a facility. Now, earlier we are talking about these 2 scenarios separately, but is it possible that we talk about these 2 at the same time, in the same setting, with the same facility? Okay, so what's the example? Well, here is one example. Suppose we are building a farmer's market, and then people like us, right? So we say, oh, this is very good, very convenient. We can buy fresh fruit, fresh vegetable very conveniently in a cheap price. Wow, that's nice. So people like it. But there are also some people who do not like it. Which kind of people? For example, there are some people who will buy an apple for $100, okay, in the high standard supermarket. So for those people, basically these fresh markets will be useless. And furthermore, it will cause a lot of problem like traffic, right? Whether environment, or very dirty or something. So basically different people may have different opinion towards the same facility. And this is the rationale behind dual preference. So assume that for the same facility, some people like it, some people hate it. Okay, and then because people may have different preferences, so they may no longer, they may not only cheat about location, they will also cheat about preference. So I may say, I don't like it, but actually I like it, right? Okay, and then so because there are more cheating options, so we have different versions. For example, as I said earlier, you can only cheat. There's some version where you can only cheat preference, and there are also some version where you can only cheat about location, and sometimes you can cheat about both, right? Okay. Now, how to define cost? Now here, and the way to define cost is the following. Now, because the people classify them into 2 categories. Now, one is does not like it, right? The other likes it. So the person who does not like it, the utility will be this. Does not like it, E equal to 0. So the farther away the facility, the better, right? The better the utility. So here we are using utility. Earlier we are using cost, right? But now we are using utility. Utility means the larger the better, right? I want to get higher utility. Okay, and then if some people like the facility, then the utility will be the length of the interval minus the distance. Okay, That means if you are very close, my utility is large, right? Okay. So when you can only misreport preference, then we show that optimal solution is strategy proof. So if you can, in other words, if you cannot misreport location, then optimal solution is strategy proof. It's basically the same as a threshold model. You pick the leftmost optimal solution and put it there, all right? And then this is strategy proof. Okay, so this is the relatively easy results. And then if you can misreport both preference and location, then we do a very interesting mapping between our model and the obnoxious model. So remember that now we have a mix, right? So some people like it, some people don't like it. So the participants' profile is mixed. That's not good. So we are doing a mapping. What kind of mapping? So let me draw an interval here. Suppose somebody is here, okay? And then actually our target is to choose either leftmost point or rightmost point. Or in other words, we are choosing either 0 or 1, okay? And if somebody is here, he likes 1. Suppose he likes the facility. And then we will map this agent to its mirror image here. All right, I map it to here. And I change his type, he hates. Now you can see earlier it's like. So if I place it at 1, it's very good for him, right? And now I change it, I change the type to hate. And then still 1 is better for this guy, right? Because I change the type to hate. 1 is very far away from this mirror image. So it's very good for this guy. Therefore, we can change all the people who like the facility to people who do not like facility to their new positions. And then it becomes an obnoxious facility location game. And then you can use the same voting method to choose which endpoint to pick, right? Okay, and then we show that, oh, using this, we can achieve a ratio of 3, or here, 1/3. And then this is also the best possible because obnoxious facility is a special case of this. So there's a lower bound of 3. Nobody can do better than 3. So here it's the same, right? So it's also a matching bound. Okay. Right. Now we move to season 3. Just now we are changing agents' preferences. So actually, I again mentioned the story about of this work, and this work is a paper with 2 authors. One is me, the other one is an undergrad student. And well, so this paper eventually is in AMAS, okay. And then so this paper is lucky because for the first time we submit, it get rejected, and then we submit to AMAS. But while I was at the conference, when I was participating in the first conference, although I don't have the paper there, not have this paper there, have another paper, I was participating at the conference and noticed there is a poster in that conference studying the same problem as us, okay? Exactly the same problem, and they're from Columbia University. And then I was very worried because definitely we finished our work earlier, we submitted earlier. It's only that we get rejected for the first time. And then on the second day, after I see the poster, I receive a notification of acceptance from the second conference. And then I feel relieved because then, well, no worry, it's already there. All right. But anyway, later on, when people refer to the works, they always need to say, oh, these 2 groups, they independently studied or initiated this model. Okay. So, but well, this paper is a bit lucky, so we don't need to argue back and forth about who discovered this earlier, right? Okay. Now, next season, we are talking about heterogeneous facilities. Now, earlier, if you have 2 facilities, for example, they assume facilities are the same, but now we can assume they are different, right? And then there are several lines of work here. One line is in our AMAS paper, the paper which contains the results of the dual preference. We also have another model. And then the other line is initiated by Serafino and Venter in their Kai and Squire paper. And then later on, we have a follow-up one that would extend their model. Let me introduce these 2 stories. Now, episode 1 is the model we studied in the same paper as the farmers market paper. Okay, so this one is a two opposite facility location game with limited distance. So what's the story? The story is the following. Suppose we have two facilities. One is like a police station. The other is a detention house or prison. Okay, and then well, I see a lot of questions. Okay, about exam. Wait for a moment after I finish the whole thing. All right. Now, these two facilities. One, people like it. The second, people do not like it. All right. Okay. So these two things, how to place them. Now, if you simply say I can place the facility anywhere, then probably I just run games separately, right? I run a game for police station, I run a game for this, then done. In reality, these two facilities, they cannot be too far away because if they are too far away, the police station will lose control of the detention house. That's not good. So there is a distance limit there. Okay, so that's why it's called the opposite facility location game with limited distance. Okay, you have a distance bound. And then the utility will be the distance to the one you don't like minus the distance to the one you like. Okay, and then I will be short in explaining the results. Basically, the results is the following. You are trying to put the facility either at the left end or the right end, and make sure that the distance is about C. All right, and then you hope the facility people like, they are relatively closer to the actual median. All right, and then we managed to prove that this kind of mechanism, if you know number of agents is even, then the ratio is over 2. Okay, and then this is also the lower bound. All right, and then when the number of agents is odd, then the approximation ratio will be n, and this is also the lower bound. So basically, we have matching bounds for the even number and odd number for this distance limited location game. All right. Okay, so this one is a bit short, right? And then the second episode is about agents may have different opinions about different facilities. So in the common in their model, common vendors model, there are two facilities, F1, F2, and then agents can like F1 only, or like F2 only, or like both. Okay, and then the cost of agents is a sum of the distances to facilities she likes. Okay, and then one further constraint: facilities can only be built on the position of agents. All right, not anywhere else. Now with this model, they have some bounds for summation of cost and also for max cost in their two papers. Okay, so what we do now, we extend their model in the following way. Now the model we do is it can be explained by every agent has a different preference. So some people say I like F1, some people say I like F2, some people say I like F1, F2, both. All right, and then I will use the example of bus station, all right, to explain our extension. So what is our model? Our model says you are going to build two bus stations, and these two bus stations, for some of them, for some people, only one of them is useful. Right? For example, I have the two lines, one is 11, the other is 99, okay? And maybe for someone, only 11 makes sense. 11 will take them from home to office. And for some of them, maybe only 99 is useful, all right? For some of them, they like both, okay? So for those who like both, or both are useful, then it still makes a difference. Why? Because you can imagine if there are two bus stops near your house, which one would you go to? Usually you will go to the closer one, right? Okay, so when people like both, then one model is called mean model. So basically in that model, we assume that the cost of agent, if he likes both, then it will be the distance to the closer facility, okay? Now the second version is what? Is when you go back from a school to home, okay? So when that happens, you may still argue I go to the closest bus stop, but probably not, because you see, if the closer bus stop, after 20 minutes, there will be a bus. And then a bit far away bus stop, after 5 minutes, there will be a bus. And your walking distance towards that bus stop is only 2 minutes. Now, when that happens, you see, definitely you will go to the farther bus stop, right? Okay, because, well, everybody is anxious to go back home. So you can go back home earlier, it'll be better, right? Yeah, so you need to check bus app, very good. You will check bus app to see which one to go to. But then you see, sometimes you have to go to the farther bus stop, right? Therefore, your cost is no longer decided by the closer bus stop. It will be decided by the farther bus stop, right? And this is the max model. Max model. Okay. And I see one question from Ziao. Which bus station the agent chooses does not depend on the distance. Yeah. I agree. Which bus station the agent chooses does not depend on distance, depend on which bus arrives earlier. But then we are preparing for the worst case scenario, right? You are, because well, in the worst case scenario, you need to go to the farther bus stop, and then your cost will be a bit high, right? Or your walking cost will be a bit high. So you want the farther away bus stop not to be too far away. Okay, you are trying to reduce that distance too. Yeah, okay, yeah, very good. So now you see, well, we have mean model and max model, right? And then remember, for the central planner, right, or the government or the decision maker, right, they need to worry about social cost or max cost. So they have two objectives. Agents have two possible cost model, mean and max. So with 2 and 2, there are altogether 4 models, right? And these 4 models, we have results for each of them, and then I will omit the details here. All right, so they are just, well, some bounds are tight, but some are not. Some don't even have a lower bound. Okay, now next episode under heterogeneous facility. So this one is not in the agenda, but also interesting. So it's called fractional preference. So what is fractional preference? Now you may imagine there are 2 facilities which can serve similar purpose. All right, for example, supermarket and convenience store. They are similar purpose. During weekdays, probably you will not go to supermarket a lot. You just go to convenience stores, grab something, okay? But in weekends, probably you have more time. You can do a lot of shopping, and then you will go to supermarket. So there will be a percentage of time you allocate to each facility, okay? So that's the so-called fractional preference, right? You like both, but you will allocate, say, 70% of time to convenience store and 30% of time to supermarket. And therefore, your cost is a weighted sum of the distance to these 2 facilities. And the same story can happen for clinic and hospital, right? So clinic is for simple things, right? Hospital is for relatively big things. Okay, and then the utility is the distance of the length of the interval minus distance to the first facility, multiplying the percentage of time you devote to the first facility, and minus distance to the second facility, multiplying the percentage of time you devote to the second facility, right? And then similarly, you can consider utility or minimum utility, these 2 criteria, right? Okay, and then we have some bounds like this, and I will also omit. Okay, now let's think again. We have changed a lot of things. We have changed the user's preference, agent's preference, right? We have changed how facilities are alike, right? And another thing we didn't change yet is objectives. What objectives? Well, social cost and max cost, right? Up to now, we only talk about these 2 objectives. Although there are also some other interesting objectives, but for example, there are some kind of a summation of square of distance, right? So there are also some objectives like that, but they are all very standard. Now, we are going to introduce 2 non-standard objectives, which are meaningful, okay? So one is called social happiness. Okay, so let me draw a figure. Now, suppose you live on the street, all right? And then suppose you live in the center. And then I'm going to build a supermarket. If I build a supermarket here, what's the cost? The cost is half distance, right? Okay, well, maybe it's okay. And let's consider another scenario. Now the house is here. Now suppose I build the facility in the center. Your cost is also half, right? Okay. Do you think these two halves mean the same thing? Or mean the same for the two agents? Now, Sharon said no, right? Why no? You see, for the first agent, this one, placing the facility here is the worst possible for it, right? It's the worst scenario. For this person, placing the facility in the middle is not too bad because he has an even worse option here, right? Okay, so basically, different people, their perspectives could be different. So now we are defining happiness as this quantity, 1 minus actual distance over worst distance. So if actual equals worst, then happiness will be 0, 1 minus 1, all right? So if actual is half the worst, then my happiness will be 50%. Okay, so even if the distance is the same in the two scenarios, their happiness degree is different, right? And we use this one to design mechanisms to minimize the social total happiness of all the people, all right, in that paper. Now, another one is about envy, all right? So what is it? The second one is happier, yes. Second one is happier because the solution is not the worst for him, right? It's not worse for him. Okay, the second one is called envy. So, well, all these are about fairness, okay? Now, why it's relevant, I'll give you one story about why the middle guy would think the solution here is not good at all. Now, you may imagine, very likely, house in the middle will be more expensive than house on the boundary because the middle house is more convenient everywhere, right? The boundary house is not convenient to those places. That's why the one who bought the middle house would have some kind of higher expectation of the actual cost, right? Because he paid more, right? So this is also one of the motivation to differentiate the so-called happiness factor for different people, right? Okay, now another one about fairness is called envy. So what is envy? Now suppose your cost is 100, everyone else's cost is 0. Would you be happy? Not quite, right? But if your cost is 100, everyone else's cost is 100, will you be happy? Very likely, right? Because everyone is the same, so you have nothing to complain, right? Okay, so that's the motivation for their work. They are trying to minimize what? Minimize the maximum cost minus the minimum cost. They hope the difference could be as small as possible, all right? Okay, and then they also use the so-called additive approximation. All right, remember when we talk about approximation, usually it's a multiplicative factor, right? Alpha times optimal, right? But they are told something like alpha plus optimal. Okay, all right? Okay, now next one. Actually, we can, well, do a lot more things. For example, we can add in constraints. This next season, season 5. We can add in constraints. What kind of constraints? For example, externality, okay? So externality, what does it mean? Now, imagine that you are building a shopping mall and you have a lot of friends, and then your utility or your gain is somehow affected by how close your friend is to the mall, not only yourself, because sometimes shopping together with a friend will be enjoyable, right? So if your friend is very, very far away from the mall, he or she is reluctant to go out, then you will also be less happy. So externality means, well, your utility is decided not only by yourself, your own distance, but also by other people's distance, okay? Your friend's distance. You need to add them together, all right? So when there is externality, there are some interesting results, okay? And then we can also add constraint on facilities like a maximum distance, right? And with this, we already did, right? But also minimum distance. The two facilities cannot be too close, right? Or exact distance. They have to be this much away from each other. And this one, we also call it activity scheduling, okay? We are scheduling an event with duration 1 hour, all right? Exactly 1 hour. So 1 hour duration event on a timeline, It can either be from 1 o'clock to 2 o'clock or 2 o'clock to 3 o'clock, right? Anyway, these two extreme points, their distance is fixed, right? You are deciding where to locate that pair, right? So this is a exact distance scenario. And also we study a scenario where the two rows of facilities and agents, they combine, they are integrated in the same thing, all right? So agent at the same time is a facility, okay? He can open the facility in his own community, and then, or he does not open it, he just go to other communities or other facilities to get service, all right? So at that time, every individual is not only an agent, but also a facility. So this is in our another almost paper in 19. Okay, and then other groups actually also have done a lot of works. For example, people also care about the so-called characterization. So basically, they show that what kind of mechanisms can be strategy-proof. They are trying to narrow down the possible strategy-proof mechanisms by saying, okay, strategy-proof mechanism has to follow this property, that property, and that property. And then mechanisms satisfy these property, they are strategy-proof. So this is so-called characterization, all right? And then people also study the so-called capacity constraint. Each facility can only serve, say, 2 people or 10 people, etc. And then there are also some other cost functions. As I mentioned, one of them is sum of square, right? SOS, and another Manhattan distance. And then false name manipulation, as I mentioned, right? What does it mean? It means that, especially in the e-voting, right? In electronic voting, people can create a lot of identities, right? Even he's only a single person, he can create a lot of identities, vote for some people, right? And then, in other words, in our setting of facilitation games, one agent can pretend to be many agents in different locations. So when this happens, as I said, the best you can do, very likely, is to choose a fixed location, all right? I do not care where your report is, okay? I just choose a fixed location to put the facility, all right? And then there are also dynamic facilities, like you have different stages. In each stage, there's one facility, and in the next stage, you can move the facility to another place, and so on, right? You try to minimize the distance over all the stages. And then there are also studies about the so-called candidate locations. So earlier, what we talked about, we allow the facilities to be anywhere, right? And now you can also say, oh, these facilities can only be placed in some locations. These locations I give you as input, okay? And then people can also do that. And then there is also something called distortion. What is that? Now, this has something to do with the ordinal preference I mentioned in the fair division, remember? Okay, okay, so now bonus point. Today we have less bonus point. What do you think distortion mean for facilitation games? Remember in the so I mentioned ordinal preference, right? In fair division, right? Okay, so what does it mean? What does distortion mean? What's the difference between ordinal and cardinal? Ordinal only have order, right? For these candidates or for these items, I have an order. I like this one next, and this one third. What's a cardinal? Cardinal means I have exact value towards each item, right? So here, similar, right? I will rank the facility positions. I like this position best, this position next, and this position third. But, well, in the cardinal setting, it means what? It means that I tell you my location, so you can calculate the exact distance from me to all the candidate locations. You can calculate that very accurately. And then distortion means what? Yeah, so you only know the order and not the exact location. Then what are the research problems or targets you may go for? Preference computation. Okay, so in order to get this one bonus, you need to know what we explained in the fair division topic. Nice try, but didn't hit the point yet. Okay. Well, here we are not talking about misreport, okay? For distortion, we do not talk about misreport. Everybody tell the truth. They just tell you the order they like the facility. okay, a position, okay? So there are several candidate positions here, 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 right? And people say, oh, one person says, I like this one best, this one next, and then this one. Imperfect information. Yes, it's imperfect information. Yeah, right. But what's the goal here? What can we do here? How to define the cost in this situation? This can only be considered as an intermediate step. Cost can still be computed based on their actual location, although I don't know it, but it's there, right? It's there. Oh, very good. Cost ratio. So I guess I will give the bonus to, yeah. Okay. Now, what's the point? The point is, if I only know the order, I can give you a mechanism, all right? But this mechanism may perform very bad for the actual realization, right? Okay, and then I'm trying to see how bad it can be, right? If I only know the order, how maybe I can do say 2 approximation, right? Compared to the worst realization of those order. Remember? So there are many possible realization, right? So for example, some people say I like this one best, and then this one next. Okay, suppose I don't have this one. And then this person can be here, can be here, can be here. As long as this is closer to him, that's a possible realization, right? Okay, among all the possible realization, which does not violate the order, how good your algorithm is, right? And then we are trying to say, oh, your algorithm divided by the optimal in all the realization, what's the worst possible that may happen, right? Alg divided by OPT, right? It's always less than or equal to alpha. And then we say the distortion is alpha. It's just a kind of approximation, right? And it can also show, if you only have the knowledge of order, you cannot do better than certain approximation, right? You cannot do better than 2 approximation, for example, right? So distortion also has lower bound. So here we are talking about the ratio, the cost ratio of the ordinal setting and the cardinal setting, right? Okay, so this is distortion. And actually, yeah, the location game also has its kind of consideration, all right? Okay, so what's more? Well, I don't know what other seasons have, you may have. Now, actually, we have some ongoing works too about fairness. This one is a submission. So basically, it talks about how to fairly treat different groups. And then in our Ichikai 2020, we have a problem studying cheating facilities, okay? Because all the previous discussion, they're about agents are cheating, right? Cheating about the location, their preference. But well, when the facilities are players, they can also cheat, all right? So we also did some work on that. Okay, now, of course, there are also many new problems that you can study. And well, those approximation ratios, many of the times they're not tight. You can try to close the gap, right? Okay, I guess this is the end of my sharing for facilitation games in the second hour. And we'll come back after 5 minutes, and then I will explain the tutorial together with the exam scope that we'll cover. Okay, see you soon. Meanwhile, feel free to ask questions. Let me get some water. Yeah. So see, about picking sequence, right? It's ABB, yes. So the order is from the most expensive or most costly item to the least costly item, okay? ABB, from the large cost to small cost. Okay, so yeah, I will talk about the scope very soon. Yeah. So basically, yeah, this question is for Cho, you see, for Cho, not for kids. Okay, And the due of in-class exercise will be next week. The current one didn't have a question on scheduling yet. Okay, so I will put that in very soon. Yeah. Okay. Yeah, maybe. Okay, whether we'll test alpha MMS in final exam. All these exam-related questions I will answer very soon. Probably I will, yeah, maybe I will briefly start the tutorial first, because final exam also relates to tutorial. So let me stop the sharing and try to download the tutorial document. Oh, okay, thank you. Yes, I believe so. I didn't turn on yet. Let me see the message. Oh, here. I see. Thank you. Now, I guess now I have turned on the original sound. Yeah, because this panel, when I'm sharing, I didn't see that option. So that's why I feel confused where the recording is. So is it better? Any difference? Okay, great. Yeah, thank you for your help. Now let me share. Let me see the PDF. To open the downloads. Okay. Yeah, tutorial 2. Now it has 3 questions. Actually, we will have another one about scheduling, which I will release soon. But for in-class exercise, it's basically optional. These parts are optional because these parts I will explain them. So definitely know the answer. And then the thing you need to do is to try to write it down by yourself, because question 2, some of you asked me, they found a proof in the paper. What should they do? They didn't think of other ways to write the proof. Well, the thing you can do is you just set a paper aside and try to recall what happens. Because last night, because I have heard about the presentation earlier, but last night I actually already forgot the proving details. Only remember the rough steps, and then I tried to figure it by myself. Fortunately, I didn't resort to the paper again to find out the proof. And then the moment I found the proof, I feel very excited because the proof is really, really elegant. This is actually for the fair division, I find many results very elegant. Okay, now let's start with the first question. VCG mechanism. So this is one thing we will test in final exam. All right, so this is something we will test for sure. We may not test this scenario. We may test other scenarios. And this is something I can tell you. But all the scenarios, they should appear already in the guest lecturer's slide. Okay, so now you know the focus to review. All right, I will not point to the specific cases of the slide. You need to find it yourself. Okay, so VCG. This scenario says everyone, 5 people, they have the value towards cake or coffee or both of them, right? For example, Alice say, oh, I like cake. If you give coffee to me, I get nothing, all right? And then you give both to me, I still only value cake, right? Only 7. And then Bob only likes coffee, right? You can see. And Dave only likes cake. And Edward only likes coffee, right? Basically, that one alone decides their value. The only exception is what? Is who? It's Carol. Carol says, if you give me cake, I'm willing to pay $0. If you give me coffee alone, I'm also willing to pay $0. But if you give me both, I'm willing to pay $14. Okay. Well, so this problem, all right, if you are the one or you are the seller, then what would you do? To whom you will give this coffee and a cake to? Okay, so I see Alice get cake, Edward get coffee. Okay, so basically you see we are trying to maximize the possible payment they are willing to pay, right? Okay, well, so this one, this combination, 7 and 10, they come up to 17, right? So actually 17 is the best the seller can ever expect anybody who is willing to pay, right? Okay, so now let's see, indeed, how much they should pay, because VCG is trying to make sure the payment will prevent misreporting, right? Because, for example, Edward can say, I'm only willing to pay $9 to coffee, and then you still give it to him, right? So how do you, right, force agents not to tell lies by using mechanisms, right? Okay, so the payment is decided by excluding that person from the game, right? So now we are doing this together, all right? Because I also is not an expert on this, so I'm doing this together with you. Now, suppose we exclude Edward from the game, and then what do you see? Oh, okay, so if you exclude Edward, and then both will go to Carol, because that is the best option, right? 14 together. And now what's the payment for Edward? How much does Edward need to pay? Okay, so Edward pay 14 minus 7. So how does this 14 minus 7 come? Okay, so basically there are two things. One is the payment is calculated based on other people's gain, right? For example, if Edward is there, other people only get 7. If Edward is not there, other people get what? 14. So without the existence of Edward, other people get more, right? Okay, so that's why, you see, in this case, Edward will pay $7, right? Okay, and then how about Alice? How about Alice? Okay, so Alice, again, if Alice is not there, again, it will go to, but not again, okay, not go to Carol. Alice is not there, it will go to Dave and Edward, right? 15, right? If Alice is there, then other people only get 10. So Alice will pay $5, right? So $5 and $7 will be the payment for these two people who get cake and a coffee, right? Okay. Well, so you are pretty familiar with this calculation process. Now VCG, well, actually computing the price and the computing allocation, basically it's relatively straightforward, right? Just like core. Oh no, sorry, just like Shapley value. A bit more complicated Shapley, but well, it's same rationale. Okay, so this is the payment you compute for the final winners. So now, second question. Discuss why Carol might have an objection to the outcome. Now this one, any idea? Yeah, so I see that someone, Sinan said ALE use less money buy a product because, well, altogether they only pay $12. But Carol said, oh, I'm willing to pay 14. Why not give them to me, right? Okay, well, so this is some phenomena that Carol may be object to, right? Okay. Okay, now there is also an intrinsic reason about this. So now you see only this Carol, she will object, right? But it seems that it does not map to any of our discussion about, for example, we can say, maybe the solution is not stable. Maybe it's not a call, right? So there are some kind of discussion like this, possibly, right? Okay, so can you somehow link this objection from Carol to core concept? Yeah, I mean, VCG is not in core. Yes, so any idea? So how to use the concept of core to justify Carol is not happy, okay? Well, if a person is not happy, you need to have some reason for that, right? Why this kind of thing is not happy? If it's only this person is not happy, then maybe it's fine, right? Because anyway, if Carol said, oh, okay, I do not play this game, then he also gets nothing, right? So why his objection is useful? Oh, okay, so very good. Now, this is a hidden bonus. Okay, now the reason is Carol and seller, they are willing to cooperate, or they are willing to deviate. Why? Because now seller gains $12. Carol gains nothing, right? He has no payment, nothing. But if Carol tells the seller, he says, okay, we too bargain. Okay, so let's deal. All right, forget about those other 4 people, and then seller can get $14, and then Carol still gets 0, but he gets something, right? He gets something, but he still gets 0, but it's fine. Anyway, they totally gain something, and seller can say, okay, maybe I will give you $1 to Carol, right? And then you're willing to deviate together with me, right? So that's why we say VCG solution may not be in the core, right? And this is one disadvantage for VCG mechanism. Okay, so any question? Okay, now if no question, I'll move on, all right? Actually, this one, I already explained the exam scope here together with this question. So I may test you on VCG mechanism on some scenario which appear on the guest speaker's lecture slide. Okay, so just get prepared, all right? Okay. Then, how to say, let me see. Picking sequence has something to do with one of the possible main challenging question. Facility location game also may link to one of the potential challenging question, right? The other two, you already know, right? One is cooperative game, call calculation, or no, sorry, value of these things. This one, I guess it will be too easy to get the points. If it is there, I hope it is there, and very likely it is there. And then the other one is approximation algorithm, all right? You may consider approximation algorithm to be the easy version because there are, yeah, I discussed with my PA a bit on this, and finally we decided to adopt a simpler version of that question because there is a more challenging version of the question. You will see very soon. And actually, for now, that question has 20 points, as usual, right? Five questions, each 20 points. But there is there may be some bonus point linked to that, okay? So then you need to guess, all right? So that bonus point is not explicitly written there. But yeah, based on what I just discussed with you, you may know what the bonus question is. Please do not send it in chat if you already figured it out, okay? So the only thing I can tell you is the bonus question is not in the question description, but feel free to write something trying to get the bonus. Although the bonus is not many, but yeah, just try to see. Yeah, I mean bonus in exam, all right? There is bonus in exam, but what's that bonus question? I cannot tell you. I can only tell you it is for the approximation algorithm question, okay? And also what we just discussed about that question. Okay, so just this much about the other questions. Now we are going to the two challenging questions, the tutorials that may serve as the building block for those two challenging questions. Okay, yeah, that one is hidden for sure, right? That one is hidden. That's all not in any calculation or any description, but it's in that approximation algorithm question. Okay. Yeah, you need to answer extra things. What extra thing? I cannot say anymore. If you want to figure out the clue, just try to watch the recording for the nearby 5 minutes. Okay, around now. Okay, so now we come to the very interesting question 2, picking sequence. Now this picking sequence, let me share the whiteboard because this has something to do with very easy calculation, but a really, really smart calculation. Yeah. So the picking sequence is 1, 2, 2, right? So they say 1, 2, 2, 1, 2, 2. Okay, now here I'm not giving any bonus because I know some of you already read the paper, so giving bonus here will be unfair. All right, I'm just trying to guide you, especially those who didn't know how to solve it, to figure out how to prove this allocation is 4/3 MMS for both people. Okay. Now, actually, the easy one. Which one is easier? 1 and 2. Argue 4/3 MMS. 1 is easier? Wow. Yeah, you are very smart. As well, actually, 2 is easier. 1 is a bit more challenging because in 1 you have to play some tricks. Otherwise, it cannot go through. But 2 is relatively straightforward. How to argue about that? You see that. So, how much did 2 get? If you look at the cycle 1, 2, 2, you see that because it's ordering. The order is C1, C2, right, and so on. So C1 is largest. So 1, 2, 2. If you do this pairing, you see 2 only get a cost at most 2/3 of the overall cost. You agree? Because you see C2, C3, both of them is less than C1, right? So 2, he didn't get the most expensive one. He got a second expensive and a third expensive one. So these 2 together with 1 for this triplet, right? You only get 2 of them. 2 smaller of them, right? And then you see, well, if you add up all the total cost, 2 will get at most 2/3 of the total cost. Is this one okay? Let me It's okay, right? Relaunch the poll, okay? This argument, okay, for 2, right? For second agent, right? Because he only get the second expensive and third expensive one. So the total cost he gets, this one is smaller than this one. This one is smaller than this one. So if you add all these 3 together, you only get 2/3, right? So if I use some more obvious values, for example, the value can be 12, 10, 8, 7, 7, 6, right? So you see that for the person 2, for agent 2, he got 10 and 8, 7 and 6. And you see, if you group these 3 together, and these 2 guys, each of them only, well, it's less than the first item. So altogether, they will be less than 2/3 of the whole thing. Yeah, or the other direction. This one is at least 1/3, right? Because it's larger than any other item, altogether 3 items. This one is larger than any other 2. So this one is larger than 1/3. Therefore, the other 2 is less than 2/3. I guess this is easier understood, right? Let me just do it again. Sorry, I do not want to see 40% of you didn't get it. That's a bit risky. Yeah. Now you know it? Oh, good. Great. I should have adopted the earlier, the opposite approach, right? Because the first item definitely larger than 1/3. So the other 2 will be less than 2/3, right? Okay. Yeah. So now I see a majority. Yeah, it's the ideal. This is ideal. So so these items are ordered according to cost from largest to smallest because it's a IDO, which means people their preference order towards these items are the same. Okay. Most costly item, most of them think is most costly item. All right. Okay. So I guess that will also make the understanding a bit smoother, right? Okay. Yeah. The worst case is they are the same, right? All of the same. Then in that case, the first item only take 1/3 and the last 2 take 2/3. That's the limit that last 2 items can go, right? The last item, 2 items can only go to 2/3. It will never go beyond that because first item is dominating, right? First item is the most expensive one, right? Okay. So now you know for agent 2, right? Almost 2/3 of the total cost. What's the relationship between this and MMS? So now we need to find a bound for MMS, right? What's the bound for MMS? Okay. MMS. Now we are finding a lower bound. So how good MMS can be? Oh, good. Yeah, proportional, very good, right? MMS can most be as good as proportional, right? Because you are dividing items into 2 bundles, right? And then you are counting the larger bundle. So the best thing that could happen is you try to balance the bundles as much as possible so that they become equal, right? Equal cost. That's best you can achieve, just like the max cost in facility location games, right? You achieve equal distance to the 2 endpoints. You move one moment to the right, then one tilt, and then that's not good, right? The max will increase. So that's why the MMS value will be at least half the total cost. So MMS2 is at least half the total. I use T, okay? Half T, all right? Now you see, the cost the agent 2 get is at most 2/3 T, right? And then MMS2 is at least 1/half T. So what's the ratio? This divided by this is exactly 4/3, right? So like Siri wrote, right? This gives us 4/3 approximation. Okay? Yeah, so that's why we say 2 seems a bit easier, right? Because you can argue how much get at most, and then how much you should get at least for MMS, and then you have the balance, right? Okay. Well, so this is one part only. Now we come to the second part. One is a bit more tricky, and also one takes me at least 5 minutes to figure out the answer last night when I fully concentrate. So let me use eraser. So one has some complicated thing. The most complicated thing comes from the first item, this item. Because one gets this first item. This first item can be very, very large. If it is very, very large, you have no way to bound it from the total value because it can dominate. For example, the total value is A, right? And then this first item can be as close to A as possible, right? Any percent possible, any percent close. So basically, this item seems very disturbing. And therefore, we are going to split this into two parts. Let me remove this one. Okay. So how much does one get? Let me write it. How much does one get? One will get the following. This item together with the other items. Okay. So suppose this item, we say it's a, let me see. T1, item 1, okay? So this is T1. It also gets some other things, all right? And these other things, we can use a similar trick to bound it, all right? Now, let's write down some formula, all right? Some formula. Maybe T1 is not so good. Let me just use A and B. That's easier. So let me just use A and B. Okay, suppose the first item is A. And the remaining item's cost is B. So basically, total is equal to A plus B. Okay. So now, what do we do? We do the following. We say, what does the first player get? The first player gets what? Get A at most A plus what? Can anyone tell me? Use a similar trick as the earlier analysis. First player get at most A plus how much B? Oh, very good, okay. 1 over 3B, okay. So that's the one I'm expecting. Why? Oh, similar reason, right? You see now, if you exclude the first item, remaining sequence is 2, 2, 1, 2, 2, 1, right? So every time one gets the last one, last item, it's a 3-item triplet, right? Okay, so since he gets last one, cost is almost 1/3 of the total cost. So this is the same argument as before, right? Because the first two items take at least 2/3. So the last item is almost 1/3. Okay, so the first player gets at most B plus B over 3. Yeah, B is the remaining items. B is the whole thing here. B is the whole thing here. All right, A is the first item. Okay. Now up to now, it's okay. Do you agree that well, player 1 will take A plus 3 over 3, and total value is A plus B? Okay, so that's what we have, right? Okay, so what is MMS? Well, why not 3 over T? Oh, because we remove the first item. Okay, we remove the first item. First item is separate. So the first item is here, right? And the remaining items, the one only get 1/3 of it. We cannot say T over 3 because, see, in the picking sequence, 1 is taking the most expensive item in every 3 triplet, right? So you have no way to bound it to be below T over 3 because it's not true. Player 1 is not getting only 1 over 3, the total cost. It's not true because player one is getting the most expensive one. And this most expensive one can be very close to the total cost. So you have no bound. Okay, good. So now let's bound MMS1. Okay, what is the bound for MMS1? So now we need to play some trick. Okay, MMS1, one of the MMS1 is the same as before because that's easy. It's at least T over 2, right? That's still true, right? That's still true. Yeah, but Xingren pointed out a very good point. Xingren said, at the same time, MMS1 is also larger than or equal to A. Why? Because eventually, in one of the bundle, you have to put item 1 in. Okay? That bundle will have a cost at least A. So your MMS can never be better than A for player 1. Do you agree? So this heavy item, right? Heaviest item. It must be the bottleneck of your MMS1 because MMS1 is taking the larger value of 2 bundles. And then the first item has to be in one of the bundle. So, right, that's a bound. And then I guess Haifeng already figured out how to do it, right? Now these two, well, actually, last night I was stuck here for a moment. The reason is, I think that it's very difficult to bound B itself because there's nothing about B here. Well, so just like Haifeng observed, this one should somehow be split into 2 parts. One part is 2/3 A. The other part is 1/3 of A, and then plus 1/3 of B. Okay, you can split these 2 terms into 2 new terms. One of them is 2/3 of A. The other one, 1/3 of A plus 1/3 of B. Now you can use the bound because A plus B is T. So this part is at most 2/3 of MMS1. And then this one is also at most 2/3 of MMS1. So you add them up together, it becomes 4/3. Right? Okay. Well, okay. Well, no worry if you are stuck there many hours because I have advantage, right? I heard the presentation. I have the memory. I'm only trying to bring back my memory. So it's unfair to compare the time. Yeah. So you see that this is really elegant, right? Xingran, yeah, sure. Please send it to me. Yeah, sure. Okay, so this is about the proof of 4/3 MMS bound. And then we will talk briefly about the exam question on this, okay? As I mentioned, exam question is on picking sequence, right? And there are 2 picking sequences. One is the IDO implied general, right? Why IDO, why some property that holds in IDO scenario will also hold in the general setting. How to transform that picking sequence to the new scenario, right? So remember that. I guess I will download the slide to explain to you a bit more. Fair division. Let me go to the respective slide. Okay, yeah. So let me stop the sharing and do a new share. Okay, can you see that? So basically, right? It says, well, if you have a prop X allocation for ideal instance, then you can design another algorithm for the general instance, right? So this part you need to know, all right? You need to know why it is this way. You need to be able to prove it, all right? Okay, so this is one thing about picking sequence, right? Another picking sequence idea is the one I just explained, right? For some picking sequence, some property, some fairness measure can be approximated in a good way, all right? So these two, both of them, you need to know it. Yes, well, you're right. You should be able to prove it, okay? Not only run it, all right? Okay, yeah, so this is one thing that I would like to tell you about the question on fair division, all right? So basically, this is it for, okay, yeah. Now let me stop the sharing and then I'll share the tutorial again. So in tutorial, there is one remaining question on facilitation games. And then if this question says, now this also comes back to the scope of the exam question on facilitation, right? And then although I will not explicitly mention that, but you could somehow guess according to your judgment, all right? So facilitation games, you see, here we are talking about the weighted version, right? So there are n agents, and then we have their locations. And what's the question? Well, the question is, if a mechanism puts the facility at x1, which means the leftmost position, is this strategy proof? And then what is the approximation ratio, right? Oh, actually, this is pretty straightforward. It's just the theorem in our paper, right? Putting the facility at x1 is how to say? Still someone remember? Putting the facility at left extreme point. Oh, 2, very good. Is it 2? Remember now we, yeah, so I guess I forgot something in the description here, all right? In the general setting, it is indeed true, all right? Let me just see the description again. Yeah, you see that you have weights. It's weighted agents, right? Weighted agents. And then the cost is weight multiplying the distance, right? Now this one is a typo, sorry. It should be W, okay? So it, oh yeah, no, so not typo. This cost already absorbed the WI here, right? Okay, so this is scenario, this is a weighted version, right? Okay, now putting the facility at x1, in our slide, we explained that putting the facility at x1 is it's not a 2 approximation, right? It's a anyone remember? Yeah, very good. Okay, it's max over mean, and not exactly. You need to plus 1 in the end, right? It's a max over mean plus 1 approximation, right? Okay, and then ask you, is there a strategy proof mechanism with a better approximation ratio? According to that slide, no, right? There's no better one. That's also the lower bound. But this tutorial question, actually is not asking about this version, the version on the slide. This question is asking about the case when W is public knowledge. I don't know whether I write that here, but so you see that with private locations, right? But not private weights. It's only private locations, okay? So, which means weight is public, but the results in the slide I showed today, they are about private weights, okay? Well, so now, therefore, the answer to this question is not no, okay? It might be yes. All right. Okay, and then Wing Chun asked, if weight is public, it's the same as non-weighted. You can say so, but but there are some, yeah, very good. So Xuejun said the weighted median. Yeah, we can do that. And well, actually, well, I also don't know the answer, but I'm trying to explore it with you, all right? If you have weight, I believe that choosing, yeah, so let me draw the figure, all right? Let me draw the figure. Putting the x1 seems not very good solution because that ratio, ratio might be too bad, right? So let me share a whiteboard, a new slide. Okay. So you may have people on different points, right? So x1, right? x1, maybe the weight on x1 is very small, like a very tiny w, and then you put it here, it's not good, right? So basically, yeah, you're right. Public means you cannot lie. So weight is public. Means, for example, this weight is 1, this weight is 10, this weight is 100, and this weight is 20, and so on, right? Okay, so one possibility is the weighted median Xuejun suggested, right? So you just split all the agents according to their weights. For example, if the weight is 10, you split into 10 agents. If weight is 100, you split into 100 weight agents. And then you median calculation based on the new set of agents, right? So in this example, for example, this is a 10. And then you know, median should be somewhere here, right? And then I just put it here. All right, is it good? Or is it better than putting the facility at 1? Now, remember, we are not talking about sum, right? We're talking about max, or weighted max, to be more accurate. Yeah, many of you think it's better, probably. You may do some computation to see what's the ratio. And then someone said, what if the position is not fixed? It's not straight proof. Oh, okay. Well, so if you, now, weighted median itself, when the weight is public, it is still straight proof. You are able to prove it. Yeah. So then, yeah, please do some calculation to see what performance weighted median has. This tutorial you need to submit it in class exercise, yes. Okay, so while I'm waiting for you to compute, all right, so I believe that the compute will be interesting too. And then I would also like to, well, to see, well, your informal feedback for the course. So you know that this course is first offered this semester. We have some slight adjustment throughout the course always. And I would like to provide the best learning experience for you. And then, yeah, also at the same time, hope that you can learn sufficient knowledge within this topic so that you can use it later on in your own research or on the course or on study. And but unavoidably, there could be some issues, right? That's very natural. And then I would like to, well, I don't know. Yeah, maybe. Yeah. So one way is to do the TLQ, but I know that something probably you would not like to write it there. So so my intention is that probably some of you, if you have some further suggestion, all right, some further suggestion about the course, you may send me email after the whole course grades is released, okay, which means that after the summer term begins. So by that time, I will not have any conflict with you. So you feel free to send me suggestions about the course, right? yeah, so this is my the favor I would like to ask you. Okay. Yeah, and also one thing that I would like to seek your opinion now is okay. One thing I would like to seek your opinion now is it did I narrow down the scope of final exam too much? So this is something that I cannot change anymore, but I would like to hear your opinion. Yeah. Xinran, you mostly should be correct on the 3 other questions. Yeah. Oh, okay. Okay, let's try it for now, right? So let's just narrow down the scope this way to see how good you perform in the end. So my expectation didn't change. I would say, yeah. So the 3 questions. So as I said, there will be 2 very easy questions, right? And then the third one actually turns out to also to be very easy, which I thought for a moment and decided to keep it this way. All right. So yeah, so that means that only there are only 2 challenging questions, and then within the 2 challenging questions, part of things are also somewhat easy. Okay. So for those, especially for those who follow all the discussions in those topics or have reviewed to sufficient depth, then getting 80 points is not difficult. Okay, so yeah. Annie is asking about third one is about VCG or matching, about VCG, not matching. Yeah, cooperative game and BCG is easy. And now the approximation algorithm seems also to be easy now. So, yeah. So just review. Okay, I will not change difficulty for sure. I already finalized the exam because I struggled for a moment, thinking maybe that approximation is too easy, but I decided to keep it this way, to keep it that way. Okay. And some of you, Bing Chun is asking about the chores in class exercise. Well, I don't know. I already forgot. I have a bad memory. So yeah, so those are the minor details that I'm expecting you to pay attention to during the class, right? So my only memory is that there will be 3 explicitly mentioned in-class exercise you need to do in my lectures. So these are only information I know. Oh, Xinran, you are very nice. Yeah. Okay. Very likely is this one. I don't. Yeah, I forgot whether it's EF1 or EFX. Yeah, it's one of them. It's on the slide. I believe you can find it. So, any conclusion from the computation of median? Oh, I mean weighted median. Yeah, so personally, I think that this computation will not be very challenging. So I probably will not go through the computation with you. Yeah, so I believe the weighted median is one possible choice to be used here. Now, of course, you also need to know how to define weighted median, right? If I have integers, it's easier. How about if I have 99.6, something like this, how to define it? So basically, weighted median mechanism also need some kind of more fine-tuned definition, right, to deal with the fractional number or even irrational numbers, etc. Yeah. Okay. And about next week, according to the schedule, we'll talk about the scheduling related mechanism design, and then we'll also have one question, some exercise, one exercise to do about that topic, and very likely, and very likely I will not. Yeah, it depends on the time, right? So to see how much we can cover. Yes, sorry. It's a good point to mention this n equal to 2. My memory vaguely suggests that it's n equal to 2 because at the time I thought n equal to 2 is very easy, but when we when we went through one round, we find that actually it's not that easy. So that's why I leave it as your exercise. So it is n equal to 2 case. But you can double check, of course. Yeah. Now, one thing I would like to remind you, yeah, so one thing I would like to remind you, next week, the materials will not be an exam, but the topic itself is also very interesting, and I believe it's more useful compared to other mechanism design scenarios, and also I believe that throughout the course we have explicit bonus, we also have implicit bonus. So this one will never change. Okay, so this pattern will never change. Okay, so this is the thing I could tell you. Okay, yeah. So I guess. Oh, okay. Yaning is asking a very good question. Do I think you will have plenty of time to get 80 in the final exam? This is a very good question. So I would expect, because now we have 3 easy questions, or maybe 2 plus 1 easy question. Anyway, I think you should have plenty of time to get 80 in the final exam. But of course, you need to do time management well, which means for easy questions, as long as you make sure it's correct, then that's it. All right, so now you need to secure the easy questions, but the time to secure the easy questions, it cannot be a lot. Okay, so now, as I said, we have easy questions, and the easy questions, the cooperative game 1 is a sure easy question, but the other 2 is not a sure easy. It's easy, but to get full mark, it may take you a bit more time depending on how quickly you can think of the solution to the seemingly challenging part. So this is what I can tell you. All right. But the seemingly challenging part is actually not challenging at all compared to the other two questions. Okay. So just be calm and review to sufficient detail. And then I believe that 80 is not a dream. Okay. Yeah, Kun, you are asking me a very good question. Will I change the type of question for cooperative game? Well, this one, yeah, so this is also something, yeah, so basically the session is over already, all right, so feel free to leave. This cooperative game, because it's easy, right? So very likely I will not change it, very likely. Yeah, but still, all right, after the exam, after the grades are released, feel free to send me further suggestion about the course. Okay. Wing Cheng, you are asking a very good question. What do you mean by change it? Definitely, I will change the values, right? That's something for sure. I cannot use the original question. Yeah. Yeah, because I know that. Yeah. Also, let me see. Yeah, I would like to see your feedback, not only from the teaching evaluation questionnaire, because that's before final. Because at that time we didn't see final yet. So I would also like to see your feedback after the grade is released or after the final exam. Also, after final exam, please do not send me any email because that will cause some conflict. Send me email after the grade is released. All right. Type, not value for many types in EP. Yeah, I think it's still some, I don't know. I already forgot because that question is made very early. It may be sharply value, I think. I don't know what's the many types. Oh, yeah, so this is a bit too detailed. I already forgot. Yes, I believe that. Yes, I believe that you will be happy. All right. Yeah, because at least you will be happy. There are now 3 easy questions, not 2. But still, I hope that it's also differentiating because easy questions does not mean you do not pay any effort. You still get 60. That's not possible, right? Because it will be unfair to the students who work very hard like you. About how to prove approximation. There are not many ways to improve that. The only way is to practice. Okay, so you may yeah, so slides is one thing. So in the slides, we have some examples, some problems where there are some kind of approximations there. And then we also tutorials with midterm. And then there are also some online resources which you can resort to. And when you see more problems, more algorithms, more ways of proof, then you will feel more confident. Now, for example, one thing I can share with you is a knapsack, right? So remember that we have an algorithm about knapsack. picking items according to the decreasing ratio of value over cost, right? Over size. So these things, they have a nice structure about the ways to argue. And then so because as I said, approximation algorithm is supposed to be the easy question in the final exam, then you should have sufficient knowledge by reading the question and then find out the clue. So that's not difficult. But if you want to say improve your chance of getting higher marks, you can also practice on possible problems that have good, easy approximation algorithms, right? Or easy to analyze approximation algorithms. Okay. Yeah, that's a very good question, Jiancong. This one I cannot say, but what I can say is you may judge according to your observation of the tutorial question, okay? So at least the final exam question will not be totally unrelated to the tutorial question. Okay, now one thing I would like to remind you, you may be required to prove both upper bounds and the lower bounds of approximation ratio for strategy proof mechanisms. Okay, so this is something I can tell you. Will season 2 plus be included? This is a bit difficult to answer, but what I can answer you is how to say? For the later seasons, right? So especially 3, 4, 5 things, I believe most likely I will not test you on that. And the probability of testing basic season will be high. So it's a randomized mechanism, right? I will choose materials from season 1 with high probability. Season 2, less, and 3, even less. Yeah, so the facilitation question will be related to approximation of objectives, that's for sure, right? So you will need to prove, for example, the max cost, the leftmost extreme point is a 2 approximation. So these things you should be able to compute it. Or like the tutorial question, right? You compute weighted median, right? So you put that weighted median, then what's the ratio of that mechanism, right? Or something like that. Yeah, so that's the rationale of that question. Okay, yeah. So follow your instinct probably to prepare for the most important point. Today's lecture actually I have already uploaded. I've uploaded PDF version actually. You can see it, right? Oh, recording. Sure, no problem. And by the way, now I mentioned earlier the bonus, right? Express bonus, hidden bonus. I guess now it's the right time that I probably give you some hint about hidden bonus. Or now I will first. So some hidden bonus is well, although it's not quite fair, but some hidden bonus is hidden after the lecture time, which is now, but that one will be a very tiny portion. So now I'm asking you a bonus question. This bonus question is explicit, okay? What do you think the hidden bonus is in the coming lecture? Yeah, my bonus question is, what is the hidden bonus in the next lecture? Oh, very good. Okay, so I already see that. Okay, yeah. Okay, that's it. I will close this session. Yes. Well, so yeah, but as I said, in order to be fair, right? So this bonus point is not, it's just a very tiny one. Okay. Oh no, not that much, right? I cannot afford to give one bonus for everyone. That's not possible. But that's a hidden bonus point. Well, sorry, okay. So it will be there. How much is it? It depends. Probably depends on your exam performance. Yeah, it's correlated. Okay. Yeah, so actually I can also tell you the reason why I only give bonus to the last lecture. Okay. Oh, but bonus cannot go into final, and I'm sure you will not only get 28, you will get double at least. So no worry. All right. Yeah. So actually the last one. Yeah, actually the last one. I can share with you my view about only giving bonus to the last lecture, but I will adopt some exception for someone who didn't go to the last lecture. I will still give bonus. Yeah. So yeah. So actually, Cliff, you you give one reason for me giving the bonus for the last lecture. That's very nice. Okay. And actually, there is another reason. Oh no. The other reason does not make much sense actually. Well, let me take it back. Maybe this is the only reason that I will give bonus to the last lecture. Yeah. Okay. Yes, it should be the average of second and third prize. Yeah. Okay. Now feel free to ask for questions further. Any other questions? Yes. Next week you need to upload in class. I remember it's so someone already mentioned it earlier. Yeah, my memory is usually not that good in remembering times. So let me just double check. Oh, okay. So So it's actually very late. In the announcement, I said it's before the final exam. Oh, okay. Wing Chong said that if someone has topped his bonus, should he still answer bonus questions? Will that bonus be lost? Yeah, actually, in general, if someone already got a full bonus, he cannot answer bonus again. I will remind him or her when the time comes. But for now, nobody topped the bonus, so everyone still has a chance. Okay. So by the way, the bonus design this year, this semester, is a 5 at most, because 10 I think is too much. It will not be healthy for the general class. Okay, so yeah, so there is still one problem unreleased yet. You're right, Jiancong. But yeah, so I will release that question. Let me see. Yeah, maybe sometime later today. Okay. Yes, in-class exercise. I mean, yeah, tutorial actually. There's one more question about next lecture's material or related material I would like to share with you. So, yeah, I will put it up there very soon. And yeah, and also I would like to mention why I tell you that the hidden bonus late today, because I believe even if I do not tell you, you will still be there in the next lecture. So telling you is not a difference. Yeah. Okay. Any other questions? Okay. So if no further questions, maybe we'll see each other again next week. And then I'll oh, you mean the final exam? Yeah, final exam, actually the passing grade is 30, but we have 3 easy questions. So passing should not be a problem for serious students. Okay, no worry. You're welcome. Okay, yeah, so see you next week. And then, yeah, I hope that you will feel next week's lecture is even more exciting. Now, although technically next week will be a bit more challenging, not like facilitation games, where you can understand the technical deductions. But for scheduling, probably it will be a bit more challenging, which also needs a bit of more focus, right? Because in the last lecture, we are trying to combine all the things we explained up to now, okay? So including approximation, online, many things. Yeah, okay. And see you next week. Thank you.